Hey, what's going on, everybody? So this is my presentation for my PhD oral defense, topic of which is complexity-based graph attention network for metamorphic malware detection. So with that, just a quick overview of malware. So according to Microsoft Threat Report, what we've known is that 70% of new threats are something called zero-day attacks. So these are attacks whereby antivirus vendors and the research community more broadly does not have an idea on these known signatures of these malwares. So that's because they're constantly evolving. So on the right here, we have a bit of an illustration of what a metamorphic malware looks like, where it has a decryption routine, a mutation engine, and its own original virus body. So the virus body is encrypted, so we can't originally see what it is until execution. But as it unencrypts itself, the mutation engine actually obfuscates it and then can repack itself again, such that the final virus body has, following mutation, is actually re-encrypted and obfuscated, so it appears different. Let me just point my laser pointer. That'll work. So with that, the malware has become more sophisticated through this metamorphic process. Therefore, simple static techniques that are only looking for a hex or a binary representation of the malware is no longer viable. So just an example of some simple scanning techniques. We have things like string, wildcards, mismatch, generic forms of detection, where pretty much you're just looking at string scanning would look for particular arrangements of the binary. Wildcards would actually introduce where you could put these question marks and sort of say, hey, I'm looking for this representation, but this can actually be anything. So it's a wildcard character. Mismatch and even generic detection, where you combine all these different forms. So mismatch just being the same thing, but in any arrangement. So malware, why we're concerned with it is that it's actually a very behavior form of execution, and it spans time and space in the topological sense. What that means is I have a cryptic.exe malware, and as time goes on, it spawns daughter processes, which are all shown in red here. And this is just to show that it spans time and space, such that time, it executes after a certain period of time, and then it sort of stops. And then space in the topological sense, in saying that all these relationships are through parent identifiers and process identifiers and parent process identifiers, where you can always follow who the parent process is. So you have your own malware sort of topology in the red, and in the green we have our benign topology. So this is just to say that there's two different avenues, metrics that we can look at. Like I said, parent identifier and parent process identifier generate this relationship. And in this example, each process is responsible for one or more event activity. So in this case, what I wanted to show was, okay, if we just looked at the registry activity of the processes, the file system, the network activity, or the thread, let's just look at that activity and also do so in the time and space sense. So this goes to research questions. Ultimately, I did this big introduction, but the question is, what are we trying to solve? Well, the first thing we want to do is we want to ask ourselves, what feature sets do we want to consider? We know a little bit about topology. We know there's events activity. So which feature sets do we want to draw from in order to classify malicious activity? Second thing is, how do we model this malware topology so we know that it executes over time and space? Okay, how can we encode that relationship? Additionally, how can we improve training through something called complexity, which doesn't make sense now, but it's a topic that I'll go through in the methodology. And additionally, how well does the model perform? So does it can identify malicious versus benign malware? And additionally, how well does it generalize to new instances? So one of our big concerns is, okay, so it does well on the data set that it's seen. Well, how well does it generalize to events and malware it's never seen before? So just quickly with methodology feature set. So this is something that was a big bulk of the work that I completed in 2021 in the latter half, which is looking at stack traces of event activity for different event types of different malware variants. And what we found was it's very effective with a very high F1 score, particularly for registry events. So what we're trying to do here is we're looking at the malware, most likely the import address table. So these are sort of the addresses on the left, and then these are some dynamically linked libraries. And then when we resolve the stack traces from these dynamically linked libraries, we can actually get the APIs that are used. And the green and the red here is just to represent, from my understanding, this was, so this is at the kernel level, and then this is at the process level, the OS level. Additionally, one thing that we did, why it was so effective, was we encoded this relationship as sort of a string of text. So similar how you can encode the understanding of a sentence and whether or not it's a positive or negative sentiment by looking at the words and the sequence of the words, we did the exact same thing with regards to malicious APIs. So if we have malicious APIs of this sequence, then we can encode this in this kind of relationship, pad it, and then we feed it into a transformer model. So back to, again, we're going to feature sets here. One possibility of how we can encode this relationship is something called bag of words, but there's alternatives. So bag of words works simply where if each of these H's corresponds to a process, we sort of ask ourselves, does this particular process use a Windows API or not? If it does, it's given a 1. If it doesn't, it's given a 0. Very simple form of encoding. But you can sort of see why this isn't that effective, and that's just because it's not encoding the relationship of the APIs used in a certain sequence, so as they're next to each other, right? So one way that we can do better is use n-grams, which is to sort of say we look at each API in sequence and we sort of put them together as a set. So if create file A and create file is used in sequence, well, then we consider that an n-gram. So we're actually looking at all the assortments of 2 or more APIs and sequences. So in this way, we're sort of capturing a little more information about the sequence, the APIs that are used in succession, as opposed to just enumerating them and then adding 1 and then incrementing them. Additionally, one of the other things we wanted to use was something called TF-IDF. So this is term frequency, inverse document frequency, or something of that effect. Ultimately, what this does is, one thing that's of concern very often is that APIs that are used by malicious actors or malicious processes are few and far between. And as a result, what you find is that it uses APIs that are used by benignware as well. So if we're paying attention to all the APIs of benignware and malware, what you find is that they use very similar APIs. So do we want to pay attention to those APIs that are used and are very routine for any running process? Or do we want to pay attention to the APIs that are used very infrequently? And that's where TF-IDF comes. So it actually, all you need to know from this expression is that it penalizes APIs that are used penalizes APIs that are used frequently and pays more attention, gives a larger weight to those that are used infrequently. And again, that's ultimately just because it's using very similar APIs, malware versus benignware, for let's just say 99% of its execution. So we want to pay attention to the APIs that are few and far between. Additionally, topology. So now we're going towards how to model malware execution, given the fact that we know there's this relationship between the parent identifier and the parent process identifier. Ultimately, what we're trying to do in this task is we want to map processes to nodes, and then we're tasked with developing an encoder which can embed relationships of this topology. So there's a lot there, but ultimately what we're trying to do is, if we consider all these different colors as different nodes, which are different processes. Again, the blue and the red can be a parent identifier and a parent process identifier. It's pointing towards its daughter process. And each of these nodes have this stack, which just represent its features. As we said in the last slide, it could be n-grams, it could be bag of words. One of the things we want to do is that we want to take all these APIs for each of these nodes and extract and in some way express these different nodes such that nodes that are very similar in behavior are close together and nodes that are dissimilar are farther apart. And that's ultimately because in machine learning and deep learning problems, all we're trying to do in the end is develop a non-linear decision boundary in some higher order space, right? So this higher order space is represented by this d-dimensional embedding space. It's d-dimensional because it can be as large as you want. And then we have different nodes. And ideally, if we have something like U and V, and U is malicious and V is benign, we want those to be located far apart, as opposed in this embedding space, as opposed to malicious nodes that have very similar behavior. We want them to be close together. So ultimately, we're trying to force them away in this higher order feature space. So that's in effect what each machine learning and deep learning model doing is propagating the features in this higher order feature space and developing a non-linear decision boundary, or linear for more simple models. And again, that's what I just said about similarity between vectors, which are closely related. And this is represented in the dot product, right? So this goes towards more of the parent process parent and the daughter process relationship, where nodes embeddings can be computed for any elf hop by building the computational graph from neighbors. So if we have in the top right here, it's a little hard to see because my face is actually blocking an orange node, but what we're trying to find here is, okay, if we wanted to gather all the information about this red node, well, what we want to do is we want its own information, right? We want to consider that. And we also want to consider the information of its neighbors. So who is red's neighbors? Blue, green, and yellow. And that's just because they're, so that's the one hop neighbor of red. Now, if we consider the neighbors of the neighbors, well, blue has a neighbor of red, so it goes back. And green has neighbors of red and orange again. Oh, red again and orange. And then yellow has red. So when you consider more and more hops, you're actually concatenating more information about its neighbors and its vicinity. And this is very important because, like we said with dynamic behavior, we just don't want to consider a single node. We want to consider, okay, so it's spawning daughter processes. What's the behavior of that daughter processes? And take that influence and tell me about node red. So that ultimately, that's what we're doing here. And this sort of aggregation is the expression for that. This is a simple feed-forward convolutional neural layer in a graph neural network, where we have H sub U, which is all that node information of a particular node. So like I was saying about the n-grams or the TF-IDF or the bag of words. So all that information is contained in H sub U. And then we have this cardinality of n, and this just refers to the neighbors. And that's just because when we aggregate this information, we want to make sure that we normalize based on the number of nodes it has. And that's just because when we aggregate all this information, if it has 100 nodes, it's going to be a very large value. But if it only has a single or two neighbors, we want to sort of account for that. So that's why it's accounting for the cardinality of the neighbors of V. Right, so it's just divided by 3 in this case for the number of nodes. And for green, the cardinality of its neighbors would only be 2 because it only has 2 neighbors. So we take this information and then we have the sum factor, and all the sum is doing is just aggregating all the information. And then we introduce a learnable weight matrix W for this particular layer. So this is where the learning comes in. And then we introduce a nonlinearity through a sigmoid or something other. And then we get our new H sub V. So originally we started with an H sub U. And then we ended up with H sub V. So H sub U is for the last layer and H sub V is for the current layer. For L. So L minus 1 to L, meaning for this current layer, what does the information contain? And that's because we need to do that computation for down here, take that information and then jump back up here and take that information, jump back there. So it's a recursive process. There's actually a few ways that people have tackled this issue with the fact that we're paying attention to, we're sort of dividing by the cardinality of the neighbors, which means that whether it be 100 or 5 neighbors, you're considering them, the importance of each equally. So one thing how we can get around that is, we still have this weight matrix W, and we multiply it by H, which is the same H over here. So this is the feature vector, but we multiply it by something called alpha IJ. So this is something that I have uncovered more so in the other written works that I've done. In this presentation, just for the sake of maybe perhaps as an appendix item, I'll discuss exactly where this alpha comes from. But this alpha is an intention coefficient, which just say is another form of computation, which just tells us, okay, so I'm paying attention to orange and red and I'm green. How much attention should I pay towards it? Should I do it 50-50, 90-10? Okay, make that as another learnable thing that I can do as part of the model. And like I said, it's a weighted sum, so it's paying attention to it. Sum, nonlinearity, everything else is the same. And I say it's in its appendix, as I had mentioned. The methodology going to complexity. So this is a very interesting concept. This is something where it's probably worthwhile to review a previous video topic, just because for the case of this presentation, this is originally 20 minutes, 20 to 25 minutes, and I really had to compress it. So this is going to be a very surface level understanding, but complexity is the concept that certain behavior exhibits self-similar behavior when examined under various scales. What does this ultimately mean in the high level things? Is that if we look at a certain behavior or a distance of something, and then we zoom in, what you tend to find is you sort of see that similar behavior, and there's a direct relationship with the measure that you're using and the scale. That's the best I could do in a sentence or two. It's a very complicated concept. Again, I have some other videos that describe it, but this slide is just to describe, it's just to illustrate that there's a few ways that we've done this in the past. One being looking at the binary encoding of malware and encoding it as an image, and then using something called the Kolmogorov fractal dimension in order to compute pretty much the entropy, the information entropy of this image, and use it in a classification. So right behind here, right under my webcam, you can actually see that this was a form of multi-class classification where I looked at various binaries, and then this information fractal dimension was looked at it, computed the entropy of different sections, and determined that based on that entropy fractal dimension that it belongs to a particular malware family. And that's just because with that original first slide where I was showing the mutation engine, that obfuscation that's done tends to have its own behavior. So it obfuscates in a very similar, consistent way. So if we can grab that information in terms of its that entropy, then we can use that in a convolutional neural network, for example, to predict a malware family. And the second thing being variance fractal dimension in a recurrent neural network. So like I was talking about that self-similarity behavior that was very difficult for me to explain. If we have some form of, I think this was internet traffic, or actually originally in this paper, all I did was some white noise. Well, white noise has a very characteristic behavior that makes it look very different than pink or brown noise. And one thing that we did in this was we looked at the regular time series, which is the blue signal, and we computed the fractal dimension of the red, which was consistent. And that's because brown, white, and pink noise has a very similar variance, right? Because it's a noise with a known variance. And then what we found was as we predicted the future behavior of this time series, when we incorporated the variance fractal dimension of that signal, we used it as a predictor for the next signal. And then ultimately what we found was better prediction when we incorporated a form of fractal dimension in predicting the time series. So ultimately what it's doing is I'm going to look at the last 100 seconds, or let's just say the last 10 signals of a time series, look at the fractal dimension of that, and use that as a feature to compute the next, whether point or next second of a time series. So it's using information about the past, long-range dependency, and using that as a feature. Again, these were both two previous works. And complexity, at least for this work, this may be a better explanation of how it's done in an informational topological sense, which is all I want you to focus on here is the red, blue, and green dots. And they're all connected, but actually they don't have to be connected for this explanation. All you need to know is that we can look at all these nodes and a subset of them further apart from a center of mass. So if the center of mass is right in the middle of these green dots, well, if I consider a certain subset green, certain subset blue and green, and then the last subset would be all of them to combine, what we're actually finding is that, again, ultimately fractal dimensions come down to self-similarity as a function of scale. So the scale here is closer and farther apart from the center of mass, and the information that's self-similar is, I'll say in a second, is the variance of the points, distance away from the center of mass. So this is a form of information topology where we're getting this information based on the topology. And then we can look at the relationships between the content at different scales, which I said is the variance, which in this case is the information contains different subsets of those. That's pretty much what I was trying to say in a nutshell. And this information is the variance. So the fractal dimension is this log-log relationship between the log of Rk, which is the scale, K1, K2, K3, that's R sub K, and then log AK. AK here is just the information, in which case what we did is the variance. So what we do is that we look at A sub K, the information, and the scale, and as the scale increases and the information, the variance of these points increases, what we find is that there's a log-log relationship. And additionally, this example shows in the X and Y Cartesian coordinates that you can compute the variance in the X and the Y dimension, but it can extrapolate to any N or D dimensional space. Variance being the square root of the standard deviation. A lot of this work was contained in 2022. So if you want the best explanation, I would to that paper, link in the description. And then incorporating it in machine learning or deep learning models is very of interest in us. And ultimately, when we're training a deep learning model, like I was saying about what exactly a graph neural network or neural networks are doing, it's creating this nonlinear decision space to separate the data in higher order feature space. So we just take a vanilla multi-layer perceptron with a certain number of hidden layers, and we have, so these are the size of neurons in each hidden layer, but we have, that would be considered 2 hidden layers because we have the initial and final. Well, the final's up here, so that's 3. What you find is that the space, which contains the normal and the malicious training examples in 2-dimensional space, looks like this. Originally, you can see that that red, if it wasn't red, it'd be very hard to discern that it's separated from this blue cluster. But ultimately, when I generated the, with a known normal distribution, this green and red, I actually created it with a different distribution just off to the right. The question just is, can the model tell the difference of these red versus these green? And then what you find is that as the model learns, what it's doing is it is forcing these training examples away from each other in a supervised classification problem. So in this space, it's very hard to discern the differences, but as the neural network stretches the surface space and projects in stretch the surface space in higher order feature space and then stretches them, then it slowly can separate them. But you can even see these red points are kind of mixed up with these green ones, and that's just because there's a lot of overlap in these clusters. But as we project it into even higher order feature space and add additional capacity in forms of neurons, then we can see the separation. And then all the way at the very end, you can see that all the red nodes cluster, and then whatever the nonlinear decision boundary is that is used for creates a boundary, let's just say around here, and then our training loss becomes 0 because it separates them perfectly, right? 100% accuracy, at least in this example, in this interpretation. But here you can see how for this particular neuron, a lot of the red points are mixed up with the green, in which case that all contributes to higher loss, lower accuracy. But this is just for a particular neuron. All these neurons are playing their part in separating this feature space, and then they're all summing up their weighted assumptions and what it's learned into the final prediction. So this is done using linear projections and activation functions, and that's because if you don't include projections and activation functions, then your final model is just going to be a sum of linear projections. So in order to introduce this nonlinearity, you need to include a sigmoid, ReLU, or some other form of activation function. So ultimately, we come down to complexity and how we actually use it in this model. So one of the things that we want to do is, so we talked a little bit about separating these features in this space and wanting to separate them. So one of the things we can do is we can actually compute the complexity through those nodes I had mentioned, and computing the variance of those nodes away from a centroid. Again, that was the complexity concept. We want to determine the complexity of this embedding space and entice the model to learn to separate those training examples. So we had our original bag of words. Just for simplicity, I've shown it here. We have a learnable set of weights here. So we get W sub H. And then through some form of feature dimensionality reduction, the reason why I say that is just because when we're talking about D-dimensional space, I can't show you a D-dimensional representation. But one thing I could do is through feature dimensionality reduction, take all that information in D-dimensional space and try your best to show it in 2 dimensions. So what do we see in an untrained versus trained model? An untrained model has all the nodes everywhere, and that's just because the weights are randomly initialized. But as a model trains, it separates those training examples. So again, this just goes back here. These are all trained models, but in a trained model, what you see is that all these red and green samples are separated from each other very well, and that's just because the weights of all these inner layers have been tuned. But originally, they're not. Everything is random. The weights are randomly assigned, right? So it's an untrained model, and we get into a trained model. Okay, so we know a little bit. Okay, so we want to capture the embedding complexity. So how is the model actually learning this? Well, one thing we can do is we can sway the model by computing the complexity in this embedding space, and then have the model feed it into the model and have the model determine on its own how much attention should I pay to this? Is it helping me or is it hindering me? If it's hindering me, then I'm going to penalize myself and not pay attention to the complexity measure. But if it's helpful, I'm going to incorporate it. So the model can learn this association of the complexity topology with the embedding space, thereby contributing to learning. And how do we do this? So we can compute it. Well, how do we feed it in? Well, at some point in the feed forward network, W transpose X, we compute the complexity in what we call a complexity layer. Ultimately, the complexity measure is D sub M. And then we just dot product or multiply it because it's a single scalar with a weight, and then feed it into the linear projection. So what is this doing? It's computing the complexity. It's multiplying by a weight that we can learn, and then it's feeding it back into the model. If the model determines that this is not useful, it's going to drive W sub M to 0. If we find it's useful, it's going to modulate the value. So as part of the conclusions and the results, we actually take a look at that and see how well it modulates this. And like I said, or driven to 0. When you drive value to 0 and include it as an addition, well then it pretty much ignores it. And I believe final slide for methodology, but maybe not, is this performance, which is the idea of the full pipeline, where we originally have a batch of feature node representation of malicious and benign training examples. Node formulation just means we gather that information about the parent and the daughter process. And these alphas, again, are just referring to that in the graph neural network expression, how much attention should we pay. So we set up those all up before learning. Node feature embeddings, where we do the bag of words, n-grams, TF-IDF, and then we initialize the weights. Graph attention is something that I don't think I fully cover unless it's in the appendix, but this is how we compute these alphas. And then we have inference. So we have another node, which is blue or red, and based on all the other nodes and the alphas we looked at, and those L hops, those first and second hops, we determine if this is a malicious or benign example. And generalization, this generalization point was just to note the fact that if we have a good model, we don't want to just learn on existing samples. We want it to learn on examples it's never seen before. The one thing we do is we represent realistic scenarios where malware is a small portion of event activity by executing on a malware sandbox. And this malware sandbox is something that has been published and described in this paper here. One of the things that we did especially for this work was we looked at a virus database that was retrieved from the Virus Total Academic API, which actually releases on a quarterly basis new malware that's been uploaded by the research community. So one of the things that we do is, what we did was for each malware example, we executed on a snapshot on a virtual machine, and then we sampled benignware with a certain probability. And this is just to say that rather than introducing human bias by executing the same benignware next to a new instance of malware on a whole bunch of training examples, it was better to sample it with a certain probability and introduce a little bit of randomness. And that's just because we don't want the model to learn that the malware is the only different thing, because all the other benignware that's executed on the host is the same three processes, right? If you're running it next to Adobe, Excel, and Dropbox, right, the model's going to learn what those three processes are, and that's just going to say anything that's not that is the malware, right? So it's not actually learning the behavior. It's just learning to remember the three benign executables. So one of the things that we did was every single time we executed, there was a random sampling of between 1 and 3 benignware to remove the sampling bias. And this is just an expression to show that there was, I don't know if it was a 13% chance, but given the number of benignware that I had at my disposal that I drew from, there's a certain chance that the benignware wasn't included in the sample. And again, just because of this randomness means that I can say from what set of benignware the example was drawn from, but I can't tell you exactly for which malicious training examples which benignware were executed, unless you look back on the snapshot, of course. So with that, I think that's a pretty good explanation. I can see my camera's in the way for this slide, but I think this is a good way to finish off at the methodology right before we get into results. And we'll leave the results to part 2 of this video series. So if you have any questions or concerns, please leave those in the comments. And thanks for watching.